also my master scissors. Okay. Wait for me. Okay, so this is my outline, and today I will divide my talk into the 3 parts. The first part, I will give you an introduction of the verification problem, and then I will focus on my research. Then finally, I will give you a conclusions for today's talk. So let's move on the
Sorry, can you move to the next page?
Hence, I don't know why is the problem in my computer. I can move to the next page.
Yes, so can you see the presentation mode?
Yes. Okay, let's move on the first part. Can everyone see my screen? I move to the next page.
Yes. Yes.
Okay. Yes. So here I want to ask a question, that is, what is the verification? And this topic is highly related to the adversarial attack. I think everyone is familiar with the adversarial attack. So here I just use one page to quickly summarize what is the adversarial attack from the attack's view and the defense view. So here we have a network. It's used for image classification and has the high accuracy. So here today, we put this image to reclassify, then it will correctly recognize that it is a cat. However, the attackers don't want to see this outcome. So they want to find the tiny noise added to this image. This image is called X, and generating a fake image as prompt. And for our human eyes, we can see that it's still as a cat. But this time, if we feed this picture to the classify, it will recognize it as a dog. So the attack is success. And here we have to notice the constraint. And we always use the Pinot metric to measure the size of the delta. And we also set the echelon as small as possible, because we want the S prime can be as close as to the X. So if today we know the ground truth is this cat, and we denote it as the EY star, it's a 1/2 vector. And if we know the target label is this dog, and we denote it as the EY target, it also a 1/2 vector. So this scenario can formulate as this formulation. That is, attack wants the output vector is an output vector from the classified Li-He-T prompt, and it wants this output vector far to the ground truth and close to the target label. So he wants this result is smaller than 0 under this constraint. But the defenders, he don't want to see this outcome. So they propose some method to protect the machines. The first one is enhance the robustness of the network. They modify the training they use the adversarial example as the training data instead of the clean data. So this time they can make the classifier more robust. And another way is use the preprocessing the adversarial example, such as this figure. Before they feed the image to the network, they first use the filter to filter out the noise from the image, so it gets a clean image to feed it to the classifier. Although these two methods can protect the machine, but there is a problem. That is, these methods do not give you the guarantee of the accuracy under their protection. So that is, if today has a attacker want to hit this network, and we still don't know the what's the accuracy under these protections of the network. So in recent years, there is another topic emerged that is certified training. In this field, people use some mathematical way to train the machine and can give you the guaranteed accuracy of the machine under the attack scheme. Another issue is the verification. And in verification, this is not related to a training. It just verify the network, what's the accuracy of a network under the attack scheme. And this is the subject of my research. So here I give you two examples to introduce the verification problem. So here we have a network and it has been trained. So now we put some clean testing data here to the network, and it has a 95% accuracy on image classifications. But we know that there are so many attackers want to hit the network. Maybe the attack A, he generates the noise and add to the clean data to get the adversarial example. And this time we can see the accuracy drops to 60%. So there may exist another attacker, attack B. He also wants to hit the network, and this time we can see the accuracy drop to 50%. And there are so many attackers, CDF, in real world want to hit the network. So our goal is to find the verified bound of the what's the accuracy of this network. Like this blue bar, we call it verified bound in the verification field. So we hope that this verified bound can be as close as to the what's the case. So tightness is important in the verification problem. So let's see the relative work. In recent years, there are so many verification methods, and they can be divided into two approaches. One is the primal approach, and another is the dual approach. In primal approach, people obtain the verified bound by forward propagation the protocol. We can see this figure. This method is proposed by IDP. How to verify the network? Here we can see that here we have a network, and their idea is first to initialize the adversarial polytope. And this adversarial polytope captures all possible adversarial examples. Then they feed this polytope into the network, and after the convolution operation, then we can get a new polytope. And we can also compute its upper bound and the lower bound. So repeating this idea, then we can finally get a lesser polytope to get its upper bound and the lower bound. And its lower bound is the verified lower bound. So according to the mathematical way to describe the adversarial polytope, we can divide it into two cases. One is the interval bound, and another is the abstract domain. And on the other hand, in dual approach, people usually formulate the verification problem as an optimization problem. And they usually find the verified bound, so the weak duality. So according to the type of the optimization problem, we can divide the problem into two cases. One is the convex problem, and another is not convex problem. So in convex problem, they use the convex hull to envelope the nonlinear function in order to make the in-output set as a convex set. So here I give you an example. This idea is proposed by Wang. Actually, it's a ReLU function here. And they use the obtuse triangle to envelope the ReLU function. So this time, the in-outputs forms the convex set. So on the other hand, let's see the non-convex problem here. So they first write the objective function, such as here, because to optimize this is a little hard. So they split it into many terms and optimize it independently. So they can find the verified lower bound. However, this work in recent years, this work mainly focuses on the verifying the ReLU-based CNN. So they have some shortage in verification of the maxpool-based CNN. And why here I emphasize the maxpool function, because the most network structures of the image classifications contain the maxpool function, such as the LeNet, AlexNet, and the VGG. So here, with this phone contains the shortage of the passive work for the maxpool function. And the first case is not applicable. The second case has the theory, but lack implementations. So here in our work, we do the experiments on maxpool-based CNN, making up the shortage of some passive work. And the shortage here we mean is the implementation. And I will verify this term in the experiment part. So let's move on the research, my research. And the first thing I will share my methods here. And in the method part, it also verify our first contribution. That is, we propose the novel idea to address the maxpool function and combine the convex outer bound trick by want. So therefore, we can verify the maxpool-based CNN. So first, let's review the problem we address. First, we consider the L-infinity non-bounding perturbation. And why we consider this kind of a metric? Because we found in recent years, there are so many attackers that to use the L-infinity norm matrix to measure the noise they generated. And the second thing is that we verify on the maxpool-based CNN. So here is a figure we can see. The architecture contains the convolution, ReLU, maxpool, and some linear operations. So how do we verify these networks is be attacked or not? So the first thing is that we initialize the input protocol. It contains all possible adversarial examples under this constraint. As we say, we consider the L-infinity norm matrix and under the echelon ball. So here you will see that the input protocol is like a square shape. Then we feed it to the network. There is a corresponding output protocol here, and we call it the echelon. So how do we verify it? we can check each point Lie prong in the Lie echelon. If it satisfies that the Lie prong is an output vector, and each point satisfies that is close to the ground truth and far to the calculable, then this will result a value that's larger than 0. But actually, we don't have to check each point one by one. We just find the worst case Lie prong in the Lie echelon. If the minimum of this equation is still larger than 0 under this constraint, then we can still verify that the network is not be attacked. However, there is the one thing we should notice. That is because the network contains the nonlinear function, such like ReLU and the mass pool. So the output polytope is like a non-convex set. It's a little hard for us to analyze the non-convex set. So here we apply the idea is proposed by Wang. They use the convex outer bounds on ReLU to deal with it. And finally, can make this set as a green convex set. And here, let's see how one deal with it on ReLU. So first, let's review that because the input polytope is a bounding set, so it implies that the output polytope after each operation is also a bounding set. So in each dimension of the output polytope, we know that it has an input region, and it may be described by the upper bound and the lower bound. So here we have a node is output from the convolution and prepared to apply the ReLU function. So we can see that its in output set is a non-convex set like this red line. So one use the convex outer bound to avoid it as a convex set. They use the 3 bounds to envelope the ReLU function like this according to the upper bound and the lower bound. And this time we can see the in output set is like this yellow region, so it's a convex set. And in the mass pool, we adopt the method we propose and combine one's idea to deal with it. I will introduce it in more detail in the next page. So through this idea, then we can finally get this green set. And this time, we will not verify this blue set. Instead, we will verify this green set. So we know that if we want to find the optimization, find the optimized solution in the green set, it's a low bound of the original problem because original problem is verify the blue set. So here in our method, we adopt the dual approach. That is, we adopt the weak duality theory. And in weak duality, the theory tells us that if the solution you found in the primal will larger than the solution you found in a dual. So this time, if the solution you found here is larger than 0, then it implies the solution you found in primal is also larger than 0. So then we can verify the network is not be attacked. So in this page, I will introduce how to deal with the mass pool function and make the output polytope as a convex set. And here I give you a toy example. This is a fully connected network. And in this network, it contains several operations. The first is a linear operation, then passing a ReLU, passing a mass pool, then finally pass the linear again. And what we care most about is here. Here is the LR2 vector, and is applying the mass pool function to get LE2. And this is the its equations here. And how do we to deal with it to make the output port as a convex set? We propose a simple idea. that is decompose the mass pool function into a multiple one-by-one comparison. So this is original function. And here, notice that because the BR2 is the output of a ReLU, so each element is non-negative. So how to use the decomposition idea of these equations? The first thing is that we take out the first element from the LR2 vector and compare with the 0, then we can get the LN21, and we use the LN21 to compare to the second element in the LR2, so then we can get the LN22. So here we repeat this operation, then finally we can still get the value of the L2. So here we can find this form. It's like the mass A and B. So mass A and B can be rewritten as A at the mass B minus A compared with the 0. So if we use this form to rewrite these equations, then we can get the form like here. Let's see this form. The first things we initialize the LN2 0 as a 0, and we use the LN2 0 to compare with the LR2 0 to get the LN21. So these equations can be rewritten as here. And if we want to write it concisely, then we can assign the results of a LR2 0 minus LN2 0 as a LR2 0. Then the second term in here can be written as the LR2 0. Finally, we add the LN2 0 to the LR2 0, then we can get the LN21. Notice that the second equations is like a ReLU function. So here we can combine the idea one proposed, that is the convex outer bound. So finally, we can make the output polytope as a convex set. So if this time we want to verify this network is be attacked or not, then we have to check the worst case of the LeNet 3. So here is its primal problem. The first is the arbitrating function that we consider worst case of the LeNet 3, and we check if LeNet 3 is close. LeNet 3, if LeNet 3 is close to the ground truth and far to the target level in the worst situation, and this results larger than 0, then we can say the network is not be attacked. And notice that there have some constraints here. The first constraint is the input polytope we mentioned before, and the second, this polytope passing the linear function, then passing the ReLU function. And here you will see that there are so many constraints in ReLU. So what happens? Let's review the equations of a ReLU function. If we get a LeNet choose vector from the linear operation, then we apply the ReLU function to get a LR2. And this is one-dimensional form. So LeNet means a node, and the LR2 also means a node. So we know that the input of LeNet can be described by the upper bound and the lower bound because its input has a region. So we can, according to a different upper lower bound, its input can be divided into a 3 cases. And the first case is that its input upper bound is smaller than 0. So in this time, we can see that its output LR2J is equal to 0. And we collect this kind of node into a I2 minus set. So here we can get the first constraint. And the second case is that the lower bounds larger than 0. So this time, the output is equal to the input. And we also collect this kind of a node into I2 plus set, so we can get this constraint. And the second case is that the lower bound smaller than 0, and its upper bound is larger than 0. And this kind, we can get that its in-output set is a non-convex set. So we use the convex outer bound to envelope it. Then we can see that in this set is the I2 set. We have 3 bounds to describe the region here. So next, we will move on the constraints in the mass pooling. So let's review the function of the mass pooling here. We can see that, as we mentioned before, this equation can be rewritten as this form because we apply the decomposition idea here. So this is the general forms to represent the mass pool function. And we can also split this form into several equations. And the first equation is we initialize the LeNet to 0 as a 0. So here we can see the constraint here. Then we get a Li bar from the LR minus Dn to get this constraint. And notice that the second constraint is that this is a Li bar apply the ReLU function and get a Li prong 2. And we know that the input can be divided by the input output bound by the upper lower bound into the 3 sets. So here we can see that we have the 3 sets here to describe the relationship between the Li bars and the Li 2. Then finally, we add the Li n to the Li prong to get a Li n 2 j minus j add 1 as a new Li n. So here we have the constraint. If we repeat these operations, then finally we can get a LeN24 and we assign it to the Li2 0. It's not, so we can still get a Li2 here. Then finally, we pass in the linear operation again to get a LeHead3 here. So let's verify the LeHead3. And here, because as I mentioned before, we use the dual approach to deal with our problem. So here I will just quickly to review that how to transfer the problem from the primal to dual. So the first thing is that we define the primal problem as here. So this problem we have already written in the previous page. So we have, and the second is that we have to define the dual variables to each primal constraint here. And if we find the if we define the dual variable, we can multiply its corresponding constraint here and add all of the term to the objective function to get the Lagrangian. So if we have a Lagrangian, then maybe then we will minimize the value of the Lagrangian over the x. This x means the primal variable. So if we minimize the value of the Lagrangian, we will get the dual function here. And we can see there is a relationship between the original problem and the dual function. And this relationship we call it the weak duality. And there has a lower bound here. So here is the primal constraints we discussed before. And here is its corresponding dual variables we defined. So if we have the constraint and the dual variables, then we can write the Lagrangian. So if we have a Lagrangian, then we can minimize the Lagrangian over this primal variable to get a dual function G like this. And this is its constraint. and its dual variables constraints. So here our goal is want to know the values of the G, but we know that he needs some dual variable here, but we don't know now. So here I will introduce how to simplify this constraint and get the dual variables to compute the function G. So let's give you a preview. That's the constraint. If the constraint simplify, it will get a network form like here. So now I will introduce how to get this back from the constraint here. Okay, let's move on it. Let's see the orange block here. So we can see the first constraint tells us the information that nu3 is equal to the minus d prime, and the minus d prime is a vector. Then if we get nu3, we will pass in the linear function to get the beta. So d prime is a vector that is the ground truth minus the target label, and recall that these two vector is one half vector. So d prime is also vector, and if you have a beta, then this constraint tells us that this is equal to the row twofold. So then we have a row twofold now, and here I use the gray color to represent the parts I have already eliminated. So let's see the, okay, here we get a row from the constraint, and then we want to use the row to get other dual variables. So the first thing is that we want to know the constraint which is related to row. So here I use the orange block to flank it, and here gives us an idea. That is, if we have a row, maybe we can get the mu n, tau n, lambda n. And if we have these dual variables, maybe we can use the second constraint, use the tau n and the lambda n to get the kappa. So then we get a kappa. And if we get a kappa, we can use this constraint to get a row by subtraction. So we get a new row here. And here we can see that a new row is also related to the second constraint here. So maybe we can get a new mu n, tau n, lambda n here. And we can find that's a finding a row and the kappa of this process forms like a circles. So if we're repeating this operation, maybe it can help us to find the all rows and the all kappas. And here we have to notice that these dual variables has a different constraint under these three sets. Why here we have a three sets? Because this constraint is related to the parts of the ReLU function in the mass pool. We know the ReLU function has the three sets because the inputs upper bounds and the lower bound. So here we also have a three set because it's corresponding to that constraint. And here we want to know the value under the bar I2 minus set and the bar I2 plus set and the bar I2 set of the mu n, tau n, lambda n, and the kappa. And in the first two sets, it's easy to compute the value of the mu n, tau n, lambda n, and the kappa because you just can use some elimination by substitution to compute this value. But in the bar I2 set, it's a little hard to use the elimination by substitution to compute it. So here I just tell you the key idea here. We use the complementary snacks to get this dual variable. So after the simplification, then we will get all dual variables. That is mu n, tau n, lambda n, and the kappa under these three sets. And what we care most about is the relationship between the rho and the kappa. So here I use the yellow block to frame the kappa. And here we write the organized form here. So now we can know the relationship between the rho and the kappa. So now we have a rho 24, and we want to know the kappa 23, and we can solve this form to get a kappa. And actually, the relationship between the rho and the kappa is a leaky ReLU. So we can get the kappa by applying the leaky ReLU here. So let's review the form we have already eliminated. The gray part is like this process. And now we eliminated the orange part. Then we get a rho 24. And if we have a rho 24, we can pass in the leaky ReLU to get a kappa 23. Then if we have a kappa 23, we can solve the subtraction to get a new rho. It's a rho 23, and the rho 23 passing the leaky ReLU again to get a new kappa here. So if we repeat these operations, then finally it looks like it works like a small network, and we can also get all kappas here. So here we use the gray color to represent the constraint we have already eliminated. So here we notice that this origin constraint, we can see that the relationship between the kappa and the nu is like a relationship between the rho and the kappa, because you can see these two forms are so similar. So here, if we already eliminate it, we can get the leaky ReLU here. So now we have the kappa, and we pass in the leaky ReLU, then we can get a new two better, and passing a linear transform to get the new one better. Then we can connect all blocks into a network forms. So now, if we want to compute the objective function J echelon, the J echelon is the organized form from the G functions. So we just have to pass, we just feed the new 3 here, and we know the new 3 is equal to the D minus D prime, and feed in to the network, then passing a linear transform to get a beta, then passing a small network to get a kappa, then passing the leaky ReLU to get a new 2. Finally, we passing a linear again to get a new 1. Then we can go get all dual variables we need here, and then we can compute the value of the J echelon. So if the J echelon is larger than 0, then we can verify that the network is not be attacked. If a J echelon is smaller than 0, then we will consider the network will be attacked. And we can use this similar idea to get a dual network. Our dual network is we called because this is all dual variable in a dual domain, and it was like a network, so we call it dual network here. And we can also the similar idea to find the dual network in the CNN. So here is the result. That is a dual network for the CNN we mentioned at the beginning. So here we also use the minus D prime scatter to fit it to the this network and get the dual variables we need to compute the objective function. Then we can also verify the network is be attacked or not. So let's move on the experiment part here. So in the experiment part, the first thing we want to know is how to know the tightness of the verified lower bound we propose. So here we design the experiments like here. Here we have the network which has been trained, and in our experiment, we train the two network. One is the CNN small and another is the CNN big, and we train them with the different training data. In CNN small, we use the ANIS, and in CNN big, we use the CIFAR-10. Then when we train the model to the high accuracy, then we use some attack scheme like the FGSN and the PGD to attack these two network. So for example, if we know the accuracy of a CNN small on testing data is 98% here, then we know that's because it's testing data and it's clean data. So this time we don't have a attack and the echelon is 0 now. So in this time, we can see that the precision of the CNN small is 98%. But if we use a test scheme to attack the network as the echelon setting larger, that is, we use a larger noise input added into the input image, then we can see that the precision will drop. So if a bound like this green verified bound we found is like this green bound, then we can say the bound is tight because it is close to the reality. However, if a bound is like this red one, then we will say the bound is loose because it's far to a reality case. So here we compare our verified bound with the other method. These methods also can give me the verified bound for the maxpool-based CNN. So we compare with the deeply, deep poly, and the refined poly. So here we have the architectures of the CNN small and the CNN big. You can see that the hidden units in the CNN big is 7 times larger than the CNN small here. And here I will give you a reason why we choose the deeply, deep poly and the refined poly as our competitors. So here let's review the list form. This form organizes the shortage of the passive works for verifying the maxpool function here. The first case is that not applicable. So in this case, we don't consider because they don't analyze the maxpool function. And the second is has the theory, but lack the implementation. And in this works, we found these 3 works provides the code, and but unfortunately, they lack the experimental evidence here. So we do our experiments on our benchmark, and we also divide these works into 2 cases in our experiment results. One is imprecise, and another is computationally costly. So here I will verify these 2 blocks in the experiment part. So before we see the results, let's quickly review the key idea of the deep poly and the refined poly. These 3 approach use the primal approach, and they use the abstract interpretations here. So originally, if we want to verify this network, the first thing we will do is to prepare the adversarial polytope here, and then feed it to the network to get the output polytope here. Then we check the output polytope formed by Y, and check if all of them are classified as A, because here we feed the image is 8 now. So we know the adversarial polytope is a high dimensional polytope. So the idea is to transfer this high dimensional polytope into the low dimension, so the abstract interpretations idea. And they also transfer the network into the abstract transform here. So this time, we will not verify the polytope formed by Y. We just verify the orange polytope here. So the difference between the deeply and the deep poly is the mathematical way to describe the this polytope. In deeply, they use the monotop to describe it, and in the deep poly, they use the polyhedra to describe this polytope. And notice that the networks may contain some nonlinear function such as the ReLU. So like here, so in the deeply and the deep poly, they also use some different convex hole to envelope the ReLU function. In deeply, they use the parallelogram to envelope the ReLU function. And in deeply, deep poly, they use the right triangle here. So let's see the refined poly. And the refined poly is the evolution version of the deep poly because the author think the bond, the intermediate bond predicted by the deep poly is not precise. So they use some optimization solver like the NILP or LP to find the tighter bond here. So let's see the results of our experiments here. The first case is the CNN small, and we use the two evaluation metrics here. The first is verify the lower bound, verify the precision of the lower bounds we predict, and the other method predict. And the second is the average verified time here. So let's see the left figure. So in left figure, we can see there are two black lines here. And this is the result of FGSN and the PGD attach the CNN small under the different echelon. And so we can see that the black line, the precision will drop here. So on the as the echelon set larger. So here we want to predict the here our method and the other method is giving the lower bound of these two black lines. So here we can see that the dark green is the deeply, and the light green is the represent the deep poly, and the serious purple lines represent the refined poly with the different NILP shaping. So orange is ours. So in this figure, we can see our bounds is this orange line, and the refined poly 3 is the other two best. That is they close to the black lines here. But let's see the red figure. It measures the average verified time here. So in these figures, we hope the time, we hope the method can spend as less time is good. So we can see that the orange line is ours, and the refined poly 3 is this line. So as the echelon setting larger, then we can see that refined poly spends 10 times larger than ours. So we can conclude that we can achieve comparable verified bond as refined poly, but we just require much less computation time here. And our methods outperform the deeply and the deep poly in both the precision and the computation cost. So here is the result for the CNN big here. And we can see we also use the two evaluation metric here. So we can see the left figure is the precision of the verified lower bound and we can see that the orange line is close to the black line, and we also cost less time on the verification here. So in this experiment, we can conclude that we outperform the deep poly, and the refined poly in both precision and the computation cost. So these two results also verify our second contribution. That is, it indicates that our proposed methods outperforms deeply and deep poly in both precision and the computation costs. We also demonstrate that our method is capable of achieving the comparable verified bond as the refined poly, but we just require less computation time. So here I want to summarize these two experiments. So the first thing, I want to explain the possible reasons why we are better than the deeply and the deep poly here. I think the key reason is the convex relaxation we choose, because we choose the obtuse triangle as our relaxation, and you can see the deeply and the deep poly choose the parallelogram and the right triangle as their convex holes, and you can see that they cause a larger arrow domains here than ours. And the second thing is the observation we want to show, that we found the verified bond predicted by each method becomes looser as the echelon increases. So we can see this yellow box here. And you can see as the echelon setting larger, the verified low bonds has a large gap between the black lines here, also in the CNN big. So here we want to know what causes this scenario in our methods, because we don't know other methods details, so we can analyze it. We just analyze our work here. So we know maybe the key reason is due to the convex relaxation, but here we want to also guess maybe it also can relate it to the loose predict bonds in the virtual map. So what is the predict bonds here? You can see these figures. If we feed the input map, we can get the virtual map after each operations. So if we have to know the nodes upper bound and the lower bound, because this information is necessary for us to execute our dual network. So we think maybe this predict bound, if it is these predict bonds are loose, may influence the results I said in this page. It's just a guess, so we have to verify it. So the next question is how to verify this guess, and how to verify the predict bonds are accurate or not. So the first thing here is that we use the upper bounds minus the lower bounds to get the bound gap of this node, and in each node we do the same things, so we can get each bound gap of each node. So if we get all bound gaps here of this feature map, then we average all bound gaps here. Then we can get this convolution feature mass average bound gap. Because this upper bound and the lower bound is our predict, so we here write the predict bounds as these green bars. So if today we can know the real bound like this blue bars here, and we can know that we can observe the gap between the predict one and the real one. If the gap is larger, then it will verify that our predict bound is inaccurate. So here is another question. That is how to get this blue bar, because this is a real upper lower bounds, and actually we don't know. So here we propose an intuitive idea to simulate the real upper-lower bound by Monte Carlo simulation here. So here, in this page, I will introduce how to get these blue bars by the Monte Carlo simulations. We know that these blue bars is formed by the upper-lower bounds. So the real upper-lower bounds maybe come from the output polytope after each operation. So how to get the output polytope in each operation? The idea is easy. Just feed the inputs adversarial polytope here, and then you will have the opportunity to get the output polytope in each operations. So here we use the Monte Carlo simulation to sample enough points to simulate this square polytope here. So here we use the 100,000 points to simulate this square polytope. And note that each point in the polytope is a figure. So it means that we feed the 100,000 images to this network here. So let's take a look on how to get the convolution bus. So assume that the convolution operation just has one kernel, so we can get the corresponding 100,000 output feature maps here from the convolution operation. So here we get the output feature maps. Then if we want to know the input, if we want to note the nodes, upper lower bounds, and then we can collect all nodes, all corresponding nodes here, and we put to here, and then we choose the maximum one as its upper bound, and choose the minimum one as its lower bound. So if we get the upper lower bound of this node, then we can compute its bound gap here. So in each node, we repeat this idea, then we can get each node's bound gap. So then we average all bound gaps here to get the average bound gap in the convolution. So in each operation, we use the similar idea to get this blue bar. But here is another question. That is these ideas can work? Maybe it cannot work and it's not feasible. So to answer these questions, we design the below experiments here. In this experiment, we consider a simple NN and consisting of only one fully connected layers. Okay, so that is we still initialize this input and simulate it by the Monte Carlo simulation. But this time, we will not feed this polytope into this network. Instead, we feed it to the one linear layer operation because this network just contains one fully connected layers. So here you will see the constraint like this. The first two constraints describes the input polytope, and we get the Li1. Then we pass in the linear operation, just one layer. So then we can get the output vector. And we want to know the output vector's upper bound and the lower bound of each node. So here we can see this problem is a convex optimization problem. So it implies its optimal solution found from the primal will equal to the optimal solution found in the dual. So if we can obtain the optimal solution, if we can obtain a solution from the Monte Carlo simulation, and if the solution is equal to the primal and the dual, then it can verify that this work can work. Here we have three approaches to find the solution of this problem. So here also use 3 different tools to find the solution. For primal, we use the CVS tool. It's a optimization solver, and in dual, we use the dual network with the RAF before. And in the Monte Carlo simulation, we just transfer this page's idea and transfer it to the code. So here we implement on the 2 different network here. The first network, it has a small input dimension, and the second network has a larger input dimension. So let's see the first network. The first network has the 3 input nodes and the 4 output nodes here. So we can see that in this figure, we can see the horizontal axis has the 4 nodes. It implies the output nodes here. And in each node, we can see that there are 3 lines here, and each line has 2 endpoints, and the lower and the upper endpoints means the upper bound found by this method, and the lower endpoints means the lower bound found by this method. So we can see that the primal is a blue line, and the dual is the green line, and the Monte Carlo simulation is the red line here. So in this case, we can see that all nodes of these 3 approach found the same upper lower bounds here. And let's see the right figure here. In this figure, we implement on the larger network. Its input contains 784 dimension, and its output just contains 4 nodes. So here we can see that the horizontal axis also has 4 nodes here. And in this figure, we can see that the Monte Carlo simulation cannot find the optimized solution as the primal and the dual. So here, giving us a conclusion that the Monte Carlo simulation method has its limits in representing the complicated details of the adversarial polytope. So we also verify our second contribution. That is, we give you a reason for the necessities of a provable robustness verification here. Because in this experiment, we show that in the larger input dimension, the Monte Carlo simulations will fail because it can simulate these so complicated details here. So we can find the verified low bound just by feeding the simulation polytope and feed into network to get the output polytope to get its verified low bound. It can work. So we have to. So the verification is necessary. So here I will give you the conclusion of today's talk. The first thing is that we propose the novel ideas to adjust the verification problems on maxpool-based CNN. And this idea is the decomposition, the maxpool function, and then we combine the convex outer bound here. So finally, we can verify the maxpool-based CNN. And the second is in the experiment parts. In experiment parts, our experiments show that we outperform than previous works, such as the deep poly, and the refined poly in both the precision and the computation times. But there is a small drawback in our network because our verified network is limited to the specific framework. That is, in our math derivations, we can the ReLU function is followed by the convolution, and the maxpool function is by the ReLU. So the network architecture is fixed. So if today you give me a network, its operation order is not like this kind, then we can help you to verify the network. So as a future work, we will focus on the precise verification on maxpool-based CNN with more flexible structures. So it's the end of my presentation. Thank you.
Thanks a lot, Jiahao. It was a great presentation and the results are very interesting. If anyone has a question, please feel free to unmute yourself and ask the question.
Okay.
Is your code base publicly available?
Can you repeat again?
I'm wondering if your code is publicly available.
Available.
Your code, like the code.
I not release now because I not publish. Maybe 3 or 4 months later.
I see. Okay. Okay, we're 10 minutes past the 1 hour. If there's no question, thanks again, Jiahao, for the great presentation. If you could please send me the slides so they can share with others, and see everyone in 2 weeks.
All right, thank you.
Thanks, great. Bye, everyone.
Okay, bye-bye.
Bye bye.
Okay.